Recently, GaN had become very popular for power electronics application because they have a huge properties like energy band gap and high electron mobilities and high breakdown field. This makes them suitable for high power and high frequency applications. For the GaN power electronics, we usually use high electron mobility transistors. In this transistor, we use two material, one high band gap air gate and one low band gallium nitride. And when they line up, the Fermi level will line up, and at the interface, there's a discontinuity over the Fermi level, and then a quantum will formed at the interface, and electron will drift to the interface and form a two-dimensional electron gas channel. And also, the material have piezoelectric and spontaneous polarizations. Okay, this is the atomic arrangement of the atoms in the structures. And we can see that we have spontaneous polarization and piezoelectric polarization. And due to the lack of inversion symmetry of outside structures and high electron activity of nitrogen atom, there's a electric field formed at the material. And at the surface, there are surface states which donor electrons. These are donor-like surface traps. So in this case, we have electrons from the surface state, and we have piezoelectric effect and the spontaneous polarization effect, and which create an electric field, which drive an electron to the 2EG area and form the 2D electron gas channel at the interface. So overall, without doping in air GaN and gallium nitride material, a formation of the 2EG formed as a result of polarization field and surface states. The gallium nitride HAM devices usually exhibit superior power device compared to the silicon-based device, which including lower specific ohm resistance and due to the 2DEG and high breakdown voltage due to the high band gap of the material. And this HAM device can be used for many different applications, from low power to high power, and because the high band gap and the high current. And they can use for many applications, okay, from commercial one to electric vehicle applications. So for the electric vehicle application, the EV can need AC/DC onboard charger, AC/DC auxiliary inverters, DC auxiliary power modules, and AC charging stations. This can also be used using the gallium nitride devices. And requirement for the power device for EV, usually we need a high breakdown voltage, and usually we require more than 1,000 volt, and we need low ohm resistance because it will reduce the power loss, and we need normally off with a threshold voltage higher than 0 because this can for safety reason and also for simple inverter control board design. And the gallium nitride HAM device start with the material growth. And in our case, we use vehicle propel, and which can provide a real-time monitor about the growth rate and the strength and the temperature. And so it will provide you with this tool. You can have a very well control the material growth. And usually for the power device, the breakdown voltage is very important. So there's quite a few ways to increase the breakdown voltage, including use the thicker layer or double heterojunction or buffer, or use carbon dop or iron dop, okay, as a chip, and also use a super lattice. Okay, so all these can be used to increase the breakdown voltage of the device. And these are typical D-mode gallium nitride on silicon HEM devices. The structure consists of the initial buffer layer and super lattice buffer and gallium nitride, aluminum gallium nitride spacer, and aluminum gallium nitride barrier, and also gallium nitride cap layer. These are typical structures of this kind of gallium nitride HEM devices, and this will provide high breakdown voltage and the high current for the device. And this is typical breakdown voltage. Okay, usually you can do aluminum gallium nitride super lattice, okay, which will increase your breakdown voltage to higher than 1000 volt. Okay, and because of the control of the stress, you can get a 6-inch crack-free gallium nitride devices. Okay, here I'm going to introduce a ferroelectric gate HEM device, which we invent in NYCU for normally off technology, okay, which is good for the future for the electric vehicle applications. Usually, for the car application, we need a normally off operation. That means you need enhanced mode devices. For this kind of devices, if you don't apply a voltage to it, the device would not turn on. Okay, so it's more safe. And so if we can have this normally off device, we can have more simplified circuit, and the power consumption will be low. Okay, and it's more safe. And for this kind of e-mode device, we need we need a high threshold voltage, usually more than 3 volt. That means unless you apply a 3 volt to the gate, the car will not turn on. And you need to have high current, and you need low on resistance to save the energy, and then you need high breakdown voltage, and also the gate leakage must be low. Okay, and also of course you need reliable devices. And this is the show you the signal. If the VTH is not high enough, then the car can be turned on due to some noise from the signal, and the car will be accidentally turned on. Okay, if the VTH is not high enough, so that's why we need very high VTH, usually higher than 3 volt for car application. And to achieve VTH higher than 3, okay, and usually for the E-mode, we have quite a huge approach in the past, okay, and which including the recess gate, the P-GaN, and foreign implantation. All this give you a positive VTH, but VTH must be high enough, okay, to prevent the accident turn on. For the 3 different kind of approach I present here, the recess gate can do high VTH, but if you do high VTH, the current can be degraded. And so usually it's difficult to achieve high VTH with high current simultaneously using this method. And I'm presenting this ferroelectric gate devices, okay, to achieve a high VTH and still you have high current. This is a view graph showing that for the conventional gate recess, okay, your current is too low, and for the usually charge trapping layer, no ferroelectric charge trapping layer, usually your VTH is not high enough. Okay, and I'm presenting this one with ferroelectric charging layers, and the concept is that with the ferroelectric you can apply a voltage. Okay, as you get applied voltage, the ferroelectric give the electric field, polarization field, which against the voltage you apply. So you need to apply even higher voltage to turn it on. Okay, that's the whole concept. So with the ferroelectric charge trap gas stack, you can get very high VTH using this device. And this ferroelectric material we use are hafnium oxide based, and usually is ALD chrome, hafnium oxide, and zirconium oxide. And if you just use hafnium or zirconium, there's no correlation, okay? And you combine them together, and you can get a good ferroelectric material, and you can get high polarization to use for the EMO application. And this kind of hafnium zirconium oxide is not new, and they are used in memory devices, and they are compatible with the CMOS with high scalable ferroelectric. So that's why we choose this material. And this is P characteristics of this material. And we know that for hafnium zirconium oxide, when the hafnium percentage 0.50%, then you get a very high correlation of 30 micron coulomb per centimeter square. So usually you have to form a crystalline, okay, phase. So this material can have good correlation. So after you form this material, you have to anneal to get good polarization. And usually the hafnium oxide doesn't have this polarization. So this is a typical device fabrication. Okay, we form ohmic and nitride passivation, get recess, and then we form the zirconium hafnium oxide ferroelectric, and after that we also do field plate, different type of field plate to make it work. So this is IV characteristics of this hafnium zirconium oxide based devices, and this device show very good VTH, like in this case 44.4 volt with 770 milliamp per millimeter. And owing to the potential barrier increase from electron trapping in the gas stack structure, it could achieve a device with very high VTH without degradation of the current. And we have tried, okay, manufacture the recess device, fluorine-based device, and ferroelectric gate devices. And the ferroelectric gate device usually can get very high current because the layer is not touching the channel, okay? So you can get simultaneously get a very high current and high VTH and high breakdown voltage using this approach. And the mechanism for approaching to achieving this high VTH is that you have put this ferroelectric layer, and then after initiation, the polarization will remain in there, okay? If you design the structure properly, and this polarization is against the electric field you apply. And so you need to apply high electric field to get a very high VTH, and that's the main reason why this device can have very high VTH. Meanwhile, the layer we don't have to recess device or do any damage to the channel region, so the current remain very high. And this is the device performance. Okay, after initiation, more electron will trap into the gate oxide and achieve device with very negative VTH, from very negative VTH to positive VTH. And there's no significant current degradation after initiation. So if you compare this ferroelectric TAM device, we make compared to other approach, okay, like gate recess, ion implant, or PGAN, you can see that this one has the high VTH, MiFi maintain very high current. And okay, so and later on we also put the field plate on it, and there's quite a huge approach. And the best one is put the source connect to the field plate, and with this you can get very high current and high breakdown voltage. So with the source connected field plate, you can see that the breakdown voltage can achieve to 860 volt. Okay, and the low breakdown handled with field plate is due to because we put a field plate, so the distance between the field plate and GaN decrease. So that's compared to no field plate is low. Okay, and when you have apply a source connected field plate, it can reduce the field and lead to achieve very high breakdown voltage for these field plate devices. And for this kind of device, after you apply a field plate to it, you can see that show very low dynamic R-on reduction, and also almost no increase of quiescent bias at 600 volt. And also you can see that on state stress test usually can be used for device output current stability. And defects and chips at the dielectric and aluminum nitride interface under on state stress could lead to the degradation of the drain current. And in this case, we don't see this kind of degradation, okay, using the field plate. Okay, this is on state stress relapse. And you can see that with stress time, okay, the source connected field plate can become very stable, and also the reduction with the current, okay, is the lowest for the source connected field plate. By conducting a multi-cycle of state retention test, device with source connected field plate show much low charge loss. For the source connected field plate sample, an average of 11% negative VTH shift was observed after 11 consecutive stress tests. This means that the ferroelectric gate devices with the source connected field plate, the performance is very good and also very stable. Okay, next I will introduce how to achieve EMO gallium nitride mixed-hem device with low speak-on resistance and high breakdown voltage for power device applications. In this case, we use tri-gate, okay, with narrow wire channels, and the narrow wire can be depleted due to the sidewall electric field, and then the 2D is depleted, okay, due to this electric field, and it resulting in high VTH, and MiFi can preserve low channel resistance. And multi-narrow wire in the tri-gate structure can provide enough current, okay, in wide tri-gate devices. This is the cross-section of the device. You can see that we have multi-layer of half-linear gallium oxide on top of aluminum oxide and half-linear oxygen nitride. And then gallium nitride using this hybrid ferroelectric charge trapping gas stack, using this configuration, can achieve high VTH with very high current. And of course, the threshold voltage can become high enough. So this is a cross-section, okay, of this tri-gate plus ferroelectric gate hemmed. So the tri-gate, okay, devices have aluminum oxide on the as and the hafnium oxide nitride as the gate oxide. Okay, and then on top of that we have ferroelectric films on the top. Okay, so with this you have tri-gate structures which can provide low channel resistance, and you have tri-gate ferroelectric gate material, which we have shown that can give you high VTH and MIFA have high IDS. So in this way, you can simultaneously achieve high VTH, high IDS with low channel resistance. So this is the cross section of this material and also the top view of the material, and we can see that the gate dielectric include of aluminum oxide, hafnium oxide nitride, and then put a ferroelectric gate on top of it. And this again a cross section of this one finger, and you can see that the multi-layer hafnium dicorium ferroelectric layer, and then on top is the gate stack. Okay, and the wire, nano wire width is about 100 nanometer, and nano gap is about 110 nanometer, and nano wire height is about 140 nanometer. And this is the device performance. Okay, you can get high VTH at 2.61, and substrate hole slope is around 73, and GM is 177. So initiation process is by applying gate source voltage at 12 volt and time 1 millisecond. So a large VTH shift, okay, for the tri-gate indicate that the strong electrostatic control caused by the trap charge in the charge storage layer for the nano wires. So in this way, you can achieve very high VTH. Okay. And the output current characteristics, you can see that the current can be 896 milliamp per millimeter, and R is around 5 micron millimeter. So this one or the approach, okay, actually give you the channel resistance quite low. Okay, and the normalized to 1 micron is about 1.01. Okay, and R is about 5.0 ohm per millimeter. So this is the lowest channel resistance for tri-gate device, indicate that the post tri-gate and with the ferroelectric gate can actually achieve low channel resistance and also high breakdown voltage and low R simultaneously. And this is the showing that the nano wire width. Okay, we have to achieve nano wire width small enough so you can deplete the channel. Okay, so you can get the EMO devices. So at 100 nanometer nano wire width, the tri-gate ferroelectric show the best device performance among the reported nano wire devices at the literature. And also, this kind of device have reasonable good breakdown voltage. In this case, we get around 788 volt breakdown voltage. So overall, the proposed tri-gate device show the lowest speed R at 0.76 milli ohm per centimeter square, and above the reported results, this is the best lowest R. And then with the breakdown voltage higher than 650 volt. Okay. So this is the comparison of device performance. You can see the threshold volt is around 2.61, R is 5.0, and R specific is 0.76. and breakdown is around 788 volt. Okay. And this is the dynamic our own characteristics. And you can see for the tri-gate, the dynamic our own dynamic increase. Okay. At a different drain voltage. Okay. So this data shows that the tri-gate are not affected by the current collapse. Okay. Next, I show some demonstration of the application of the GaN and SiC device for power switching applications. Okay, this is a 120 millimeter GaN and SiC MIS-HAM device we're using. And this is a typical performance with the output current higher than 60 amp and the breakdown voltage over 1200 volt. And this is the device we use to make the power modules. And here I'm showing two big power conversion applications. One is point of load converter, and one is fast charger, and one high power charger for EV, and wireless charger. Another emerging application for GaN HAMD is a driver for the laser source of LiDAR. And in this case, we use HAMD as the driver because it had high power and high speed. So which enable the LiDAR to operate at high speed and with higher power. Present a few examples of D-mode galvanized HAMD cascode. And the reason we use this approach is because the simplicity, innovative cascode D-mode GaN HAMD, which have a small output capacitance, and it's low cost. It reduces the need of AMR in typical converter design, and high voltage GaN HAMD owns a large breakdown capability, dual inductor charging, and cascode modes does not need high breakdown voltage, and is high efficiency due to the low on loss and the small size due to high frequency operation. So this is an example synchronous buck. Okay, in this example, new galvanized HAMD based device use P cascode galvanized HAMD and to make this synchronous buck converter circuit realized, and the efficiency is 98%. Okay, the next example is wireless power transfer, and this wireless power transfer is using Class E amplifier, and with 100 watt, it can transmit up to 50 centimeter, and at present we can do up to 2.0 meter. Okay, the next example is variable frequency pulse width modulation circuits for redundant wireless power transmitter, and it can work at a 50 megahertz and can be used for LiDAR driver. And then the next example is Class E amplifier, and this one actually is for wireless transfer application, and it's very low cost. According to our estimation, this year we can make it like 1.5 USD per piece. And finally, the flyback converters, and it can use for AC/DC converter, and the example we have is a 65 watt and efficiency is up to 98%. Finally, I'd like to conclude the talk. I have shown that GaN and SiC electronics will play an important role for power switching applications, and GaN and SiC HAMD on silicon have high breakdown if you properly design the buffer layers. Okay, so the breakdown voltage can be 1000 volt and above. And the GaN and SiC ferroelectric gate HAMT, we demonstrate with a hybrid ferroelectric charge trap. Gas stack shows the best EMO device performance with high voltage and high breakdown and high current. And we have also demonstrated a tri-gate ferroelectric HAMT, which have a low channel resistance and demonstrate a high voltage of 2.61 and breakdown more than 650 volt. This is the lowest on channel resistance reported so far for EMO devices. And gallium high nitride have demonstrated for fast charger, wireless charger, point of load converter, high power charger, and finally, we have predict that the LiDAR application using gallium nitride HAMT as driver could be very promising for future potential applications. Thank you for your attention. This concludes my talk.